database management. In this module, we focus on the relational database model. Now that we have zeroed in on relational databases, let's take a look under the hood. In this module, we will explore both conceptual and logical physical database components. First, we will look at entities, attributes, relationships, and business rules, because before we get ready to build anything, we better understand what we're supposed to build. This means talking to a whole lot of people in the organization who are later going to use our database. And that's what we need conceptual design for. Later, when we are sure that the database we have designed does what our internal customers need it to do, we can start transforming our conceptual design to a technical design based on which our engineers can actually build the database. At that point, we're talking about tables, columns, and data types, constraints, and views. We will also discuss the most common sources of errors when dealing with referential constraints and integrity constraints. We start our journey into database architecture with conceptual database design. Conceptual database design is the process that creates a technology-independent data model that can be implemented on any database, or even on a flat file system. What this looks like is what you see on the right side here. This is the famous entity relationship diagram. In this diagram, we see the things or business realities that our clients have asked us to model. These entities appear in the rectangles. They are connected with the also famous crow's foot notation that describes how the entities are related. At this point, our conceptual design describes a model of the reality that our clients need to manage. What it does not describe, and that's not its job, is the type of database management system, the software on which the model is implemented. We should be able to take this model and build it on any DBMS, from MySQL to MongoDB and even Neo4j. Whenever people think about a database, they tend to think about it in terms of what data they're going to manage. In other words, we're talking about what things we're going to model or represent in our database. These things are called entities. An entity can be customer, employee, product, and so on. Anything, literally anything about which we want to collect data. Entities can be internal and external. Unless we're working with complicated APIs, we model primarily internal entities. As you can see in the graphic to the right here, entities are represented by a rectangle and named with a noun. If we are modeling an entity, we want to describe its characteristics. For that, we use attributes. For example, for our customer entity, we want to collect attribute values such as the customer's name, their address, city, country, and phone number. For our product entity, we're interested in the product name, its category, unit price, and so on. There are two major types of attributes, unique and non-unique ones. In a well-constructed database, each table row carries a unique designator, or ID. That's what we call the table's primary key. Primary keys make it easy to find any row in a table because no two values are the same. As we can see here, primary keys show up in their own rectangle on the top of the attribute list. In contrast, we can have attributes whose values repeat, such as city, for example, or product category. These are non-unique and they are useful for grouping or aggregating data. The final component in a relational database architecture is, well, the relationships. Relationships define how entities are connected. As you can see here, there's a special kind of notation. We call this notation crow's foot notation. Crow's foot notation shows in a very intuitive way the cardinality of a relationship. Cardinality describes how many instances of an entity another entity can connect with. Cardinality makes or breaks a good database. There are essentially two allowable cardinalities, one-to-one and many-to-one. An example of a one-to-one relationship would be that one employee works for one company, but one company can have many employees. That is an example for a one-to-many relationship. With cardinality, we always need to define each end of the relationship. Cardinality describes the maximum connections that a relationship can sustain. Ordinality describes the minimum end of a relationship, typically 1 or 0. If a relationship is marked with 1, it is mandatory, such as an employee has to work for one company. And if a relationship is 0, a relationship is optional, such as an employee can have 0 or 1 company cars, and 0 or many assigned electronic devices such as a desktop computer, a company desk phone, a company cell phone, a laptop for traveling, and so on. Setting up relationships between entities is the hardest part of architecting a database. They have to be specific, efficient, and scalable. That's why good architects pull in the biggest paychecks. Here is an example of a one-to-one relationship. The straight line between customer and account receivable shows us the cardinality, namely that each customer is connected to one account. The two little vertical lines on each end mean that it is absolutely mandatory that each customer have no more than one account number and that each account number is assigned to one and only one customer. Here's another example of a one-to-one relationship. The connection between employee and company car. But check this out. An automobile can be assigned to 0 or 1 employees, and an employee isn't suddenly not an employee anymore if she isn't assigned a company car. In our example, the relationship between customer and order ID is one-to-many. This means that an order must be associated with one customer, but more than that, with one and only one customer. But a customer can place 0 or many orders. In other words, we're not dropping any customer from our database just because she doesn't happen to have an order currently processing. Again, we look at both sides of the cardinality to determine the ordinality. Because we're always coming back to finding an individual data record or specific data item, many-to-many relationships, like the one between product and order, are problematic. Now, we know that an order typically contains one or more products, and a product can show up in any number of orders. So, since many orders can contain many products, how do we make that relationship so specific that we can find the one order in which a particular customer has ordered a particular product? With a many-to-many relationship, we can't. That's why we need to avoid them, and wherever we see them, we need to break them up into a set of many-to-one relationships that are connected with what we call an intersection table. In an intersection table, we find attributes that allow us to turn the many-to-many relationships into two many-to-one relationships, like here with unit price that comes from product and with quantity discount that could be applied specific to each order. Intersection tables allow us to break each many-to-many relationship up so that it can fit into a relational architecture. Cool! One more relationship that is important, especially in organizations, is the recursive relationship. You can see that there are two ID attributes here. One is the employee ID, which happens to be the unique attribute and primary key here, since all employees have one of these. The other one is the manager ID, which would contain the employee IDs of those employees that are also managers. And they would be in the manager ID attribute of the people they supervise. That way, you can relate the regular employees to their managers without much effort. As you can see in the upper right corner here, the relationship is that an employee can have 0 or 1 managers, and that a manager can have 0 or many employees in their department. Speaking of relationships, Is it always that way, that an employee has 0 or 1 company car, and that a company car is assigned to 0 or 1 employee? Can company cars be driven by a number of employees, and perhaps a company won't need to keep a car if 0 employees drive it? What about orders? What if a number of employees pack an order instead of just one? Who gets to decide that? The quick answer is not you, the database architect. The longer answer is whoever makes the policies in an organization. That can be an executive level manager or a business manager, even a business analyst or data architect whose job it is to communicate to you the most important thing in database architecture: business rules. Business rules describe the relationships and constraints that organizational policies place on data and data models. We describe these business rules at a technical level in the relationships that we set up between entities in our database. As we make our way from the conceptual model to the logical model, that is, the model that developers can now use to develop the code that describes the actual physical model of the database, we need to remember that while conceptual models are universal, logical models are specific to the chosen database management system. While a conceptual model, graphed as an entity relationship diagram or ERD, describes general relationships between entities but is really DBMS agnostic, a logical model is DBMS specific and translates entities into tables and attributes into columns. It is still built on rectangles and primary keys, and we will talk in more detail about the differences between the conceptual and the logical model later in this course. The logical model leads directly into the physical model, which is nothing else than the SQL code that describes the logical arrangement of tables and relationships. This is the code that you're seeing in the gray box here. Relational databases consist of tables. Typically, a table represents one entity. It is a two-dimensional arrangement of columns and rows, where the columns are the attributes and the rows contain all the data values. This means, too, that the rows are really instantiations of the table in the same way in which objects are instantiations of a class. Tables are stored in the table space, whose size is usually configured not to exceed the physical space on a hard drive. If it does anyway, you will see table insertion errors. Since tables are the basic building blocks of a database, it is important to get their naming convention right. That is because in many cases, a database doesn't stay on its own and has to interface with a number of other databases in a distributed system. That's why there are some best practices for naming the tables in your database. They are using only uppercase, no mixed case names. Don't use any spaces, but use underscores instead. And follow organizational standards regarding singular and plural. You really want to design your database as universal as possible. That's why sticking to these conventions will help you build a more scalable system. There are many poorly designed databases out there. This is why it can sometimes become necessary to redesign the structure without changing anything. Views are a great way of doing that. Not only can we use views to aggregate the data that an external user can see and shield the data from them that they are not supposed to see. A view or a set of views can also be a way to build a virtual table structure on top of an actual table structure that is poorly designed, often for the sake of lookup efficiency. Note that a view is kind of like Schrödinger's cat. It does and it does not exist. That is, it looks like a table, but it exists only as a stored SQL query. So each time you call the view up, the stored query will execute and deliver to you the view that you would like to see. But it looks like a table, yet it isn't a table. When we build a relational database, the physical model, that is the SQL code, requires that we specify not just the type of data that we want to store, such as integer or character or variable character or date and time or a timestamp or a list, but also the length of the field. So for example, when storing American zip codes, I have to specify as I set up the attribute that this attribute is 5 digits long. If at any point zip codes become numbers with 6 digits, that requires some major re-architecting of my column. The same is true for any string attributes like character or variable character. Length matters. The last aspect of the physical data model we need to talk about is constraints. Constraints determine the available values for an attribute. Referential constraints ensure that an attribute that signifies importance and uniqueness in a table and points to another table is, for example, never empty, and that its value matches the value in the target table to which it points. The unique non-null value in the parent table is called the primary key. For example, customer ID. We can use this value in the target table in order to pull in all the values in that row with the key in the parent table. We do that by using a foreign key. If, for example, I want to know all about my customer who has placed an order, I will carry the customer ID, which is a primary key in the customer table, along with the order in my order table. That way, I can always take that customer ID in the order table and look up the row with that number in the customer table. This is how I always have access to the customer information for each order, but I can travel lightly and just take the customer ID as foreign key on my order ride. Referential constraints are great. However, they can also easily lead to errors if the parent table, that's the one with the primary key, does not contain the row you're trying to reference, as you are inserting information into the table with the foreign key. In fact, that is probably the most frequent error. Secondly, the values for all foreign keys must exist in the parent table. If they don't, you can't look them up, and there's another error. The same goes for deletions. If you delete a row with a primary key in it from the parent table, all the rows in any other tables that reference this primary key in their foreign key column must also be deleted. Referential constraint errors can be hard to track down and can look pretty scary. It's important to remember that you can't reference something that doesn't exist. That can make tracking down the missing primary key easier. A second large area of constraints is called integrity constraints. Different than referential constraints, integrity constraints don't monitor whether a value in the child table also shows up in the parent table. An integrity constraint checks the integrity of values based on the rules you specify, and only on the table for which you specify those rules. Take not null, for example. Try inserting a row that is missing a value for a not null field. How about if you're checking the value in a particular field against an allowable list of values, similar to a drop-down menu, and the value you want to insert is not on the list or doesn't fit the math? That is because little programs called triggers can be launched based on the values that are being inserted into particular fields. And if those values aren't right, the little program or trigger won't execute. And we know what that means. Most likely, you will see some of these errors as you work on your database in this course. Know that while constraints can be somewhat painful to deal with, especially if you're stepping into a database that you've inherited from someone else, that the easiest thing is to follow the bunny trail of referentiality. So let's take a look at what we've covered in our journey through the relational model. We have defined what the conceptual database design components are, including entities, attributes, relationships, and business rules, and we have talked about who makes the business rules and who follows them. Then we have looked at logical physical database design components, including tables, columns, and data types, and views, and constraints, and we've talked about the most common sources of error when it comes to referential and integrity constraints. All of this should set you up for success in your database future.